The first presentation of this inversion session is by Yaoguo Li, and the title is An Overview of Airborne Gravity Gradiometry Data Inversion. Yaoguo received his BSc in Geophysics from the Wuhan College of Geology in 1983 and a PhD in Geophysics from the University of BC in 1992. He is currently a professor in the Department of Geophysics of the Colorado School of Mines and leads the Center for Gravity, Electrical and Magnetic Solutions and the Gravity and Magnetics Research Consortium. His research interests include inverse theory, inversion of gravity, magnetic and EM data, geology differentiation and their applications to resource exploration and production problems. Please welcome Yaoguo.
Thanks, Terry. Good afternoon, everyone. So it's a real pleasure to be back to ASEG in general, also back to this workshop. My talk with a bit of a subtitle would be the evaluation of information content through quantitative inversion, namely using the quantitative interpretation, namely using the inversion as the tool. My co-authors are Suresh Martinez, who is working with USGS now, and one of my PhD students, Joe Capriati. So I would like to first acknowledge the organizing committee. I know it's a lot of effort and coordinating, and again, appreciate the opportunity to come here and present something on the inversion, which actually now becomes somewhat ubiquitous in terms of quantitative interpretation. And one particular person I would like to acknowledge is Marco Braga from Valley, who has since moved on to university, and he actually played instrumental role in terms of what our groups have been doing with the mineral exploration related application of gravity gradiometry. Of course, a lot of contribution from other members group, and research has been funded by the GMRC sponsors, some of the representatives sitting in the room here. So very brief outline. I'll talk a little bit about background. When Mark and Richard first invited me to give this, I thought, great, I love inversion. I'm going to come here, give a review talk. Then very soon I realized, as I mentioned, inversion is so ubiquitous now. It's so well developed. I personally no longer think there is really need or room for inversion overview. It's a tool, and I will come a bit more on that. So what's more important is what we can use this tool and several tools to pull out as far as useful information from the airborne gravity gradiometry data for the exploration purposes. So that's what I'm going to focus on by presenting three brief case studies listed here. Then I'll draw a bit of conclusion. Hopefully it's not too controversial, and I think it's really encouraging because by the end I put all this together, realized it's quite encouraging. So status of gravity gradiometry inversion, I think it's fair to say it's a fairly mature subject, and it's as mature as any other potential field data inversion. So the reason I say this is for first is physical understanding. We've been working with gravity in exploration community forever, since the beginning of the field. We understand the physics, computation, everything. The mathematical intuition of gravity gradiometry data, its behavior, spatial change, it really comes from the Poisson's relation and all the experience we as a community have on the magnetic data. Mathematically, those two data sets behave exactly the same. And the processing and develop techniques are well understood and developed over the last 10, 15 years. As some of the presentations show this morning, that makes point. Then of course, inversion itself as a tool, the methodology, understanding, and computational now in our community is widely available. So in that sense, it's actually quite exciting. Means that we don't need to face the hurdle of doing the inversion or developing tools. We can look beyond that and apply it to see how we can solve the problem. One thing I want to mention is that since it's been 6 years since we last had this workshop, is that it's fair also to say that anyone who has a magnetic form-modeling inversion code can probably generate a gravity gradiometry code in half an hour. I think it's just like that. All the components are in there. I still want to emphasize this point because that's actually how we should be working and for efficient purposes. The other part is in terms of tools, implementation, algorithm, software, it's a lot available in the community. It's a huge number, so I'm not going to go into it, except to comment there are 3 types of parameterization. We do generalized inversion for density. We do generalized inversion for the boundary or base of salt, basement, or we do mixed parameterization. All 3 have their different purposes, and so this is a brief list of all the, not all, but a very small segment of the publication you can find. The way I picked this is more biased towards my, what I'm familiar with in terms of the inversion, namely the density inversion and interface inversion, and also showcasing some of the latest development. But there's a large number of publications in the literature. A lot of these have been implemented and available in some form and some channel for explorationists. So therefore, going back to my comment earlier, a more pertinent question and perhaps a more practical question is, what is the information content in the current gravity gradiometry data that we can extract and make use to solve exploration problems? So in this presentation, I take the approach of examining what we can get out of this data by doing the inversion, in particular doing the density inversion. That's what we as a group are good at it, so that's what we've been focusing on. So a bit of comment on the inversion code we're using for that produced all the results I'm going to show. It's regularized density inversion, single parameter type. We use L2 model object function, or the other types available, and we have reference model capability, bound constraints, and we also include low pass filter. I think I got one A missing. Low pass acquisition filter, which is actually prompted by, quite fittingly, by the work done by Joe Sands, Australia, and Richard. We actually had a collaboration on this. And of course, fast computation using wavelet compression for sensitivity. That was derived from the magnetic inversion. So onto the details of 3 case study. This is iron ore exploration, hematite, in Brazil, in the Minas Gerais state, and in particular iron quadrangle. I cannot quite pronounce the name as Suresh will do. So the whole idea is looking for the soft hematite, and in other settings, what we have is the iron formation is pre-Cambrian age and holds in the syncline situation, and it's structure controlled. So this is the area we're going to look at for the data. We're going to focus on the northern part of this. This is the work that Suresh did in her PhD thesis, and we had a publication on this. So for brevity, this is the plot of data, 6 components, after terrain correction with standard 2.67 terrain density. Just a bit of detail on the inversion. So we use 25 by 25 by 20 meter digitization, fully incorporating the topography. So that's pretty much common model size for detailed inversion with bound constraint 0 to 4 because we're looking at the high density hematite region reference model. Then a bit of smoothness, that's not so crucial in this case. Just an example for the inversion and observed data, namely this terrain corrected, predict data and the residual, just give you a sense of the level of the residual we have and the signal we extract and the randomness. Pretty much this is, we're confident all the signal we can extract from data extracted. So this is a simple, just a visual illustration of the density model we got. And with cutoff point 8 gram per cc, corresponding by and large the presence of hematite distribution. In fact, we have operating mine here, or a valley, and also have cross sections here to validate this. One comment I want to make is that if you invert one component, that actually recovers majority of density structure. And adding other components actually gives you more like a secondary, so it's a qualitatively speaking, secondary level, second order detail improvement. So that I think that relates to the information content of data. The reason is we have discrete sample data, multiple components with noise. Therefore, additional components would add some minor information, but not dominantly amount there. So quick summary in this case is that inversion of gradiometry data was done on the deposit scale. It was able to delineate the hematite distribution, and result is highly consistent with known geology. And as I mentioned, one component recovers major density distribution, and additional components refines result. So that really depends, reason that's relevant is depends on what the purpose of the inversion is, and how the data or results can be used subsequently. So move on to second case study that's closer to home here, R.J. Smith's test range. So in this case, we're looking at is trying to understand the information content in terms of one thing that's often discussed here in the community also that came up in the morning is the different spectral content. So commonly, it's assumed that because of noise, well, I would not say commonly, at least years ago, at least around the last workshop, 6 years ago, you often hear the comment that the Airborne gravity gradiometry data, the noise level is such that we don't have enough shortwave lengths information to do the detailed exploration. That's one thing that made such impression on me. It took me years to actually get out of that. Other part, of course, that again showed up this morning is the long wavelength component. So I think the first case study shows that there's sufficient short wavelengths to do the exploration detailed work. But then next question is, okay, what about the long wavelengths feature? So this one is work done by Joe Capriati. Look at the test range data. There, as we know, we have fantastic ground data, and so that can be can serve as ground truth. And then there are other data sets in here. In particular, we focused on the Airborne Falcon data. That data set is fantastic. We're just talking about when CC initially did processing and compared the result with the ground data, we got about estimate 2.5 average error noise. We got a lot of flack for that because as time, people thought the noise level is much higher. But of course, we convinced that level, and also that number was corroborated by work later on done independent method by Mark and Ash Brown. So in this case, what Joe did was and took the ground gravity data. These are detailed inversion as best as we can. So this would be the ground truth in terms of inversion. So we're trying to compare things on the same level. So this perhaps actually will get Des going. We don't know the geology, but we know the best inversion we can do from this dense ground gravity data. So that would be the level of comparison. Now what happens if you take the Falcon data, as good as they are, you do the inversion, you get a model that actually is not quite what you would expect. So in this case, it's losing long wavelength component, and because of that part of signal is not resolved, so it affects the partitioning of the signal information content in the data. Therefore, you end up with really smooth, broad-looking density model. Again, we use the same cutoff level just for the comparison. Now, what happens is, in this case, we have the ground data, or also later on, realize there are airborne gravity data. So the point is that if you have very sparse gravity data, doesn't have to be very dense, just enough to supply long wavelength components. So in this case, what Joe did is took the ground data, grossly downsampled or just extracted a few points shown in these white stars, used that to do the joint inversion of the Falcon data and the sparse gravity data to supply the long wavelengths information. So result is showing here. So interestingly, the kind of fixing of the long wavelengths signal in the data, helps to repartition the signal so that actually you get a much better resolution in the shallow part. In fact, the opposite is true as well in general, but we don't have example here. So if you compare the result, the inversion result from the ground gravity data, very dense, highest quality we can have in this case, and also the joint inversion of TXY and TUV and the sparse gravity data. You look at these two models with same cutoff level, they're highly consistent. So that says with very small number of sparse gravity data that put in the joint inversion, then those small number of gravity data is able to provide the required long wavelength information to get the data that gets information that's comparable to what you can get from very dense ground gravity data. So that's very exciting to us, at least from our standpoint. So summary for this section is that joint density inversion of multiple data sets. We can do that with, in this case, especially with, also it makes sense because two data sets have very disparate information content or spectral content. So the measured Falcon components can be integrated with vertical gravity data. That's a given in the community, except in this case we have a particular algorithm geared towards this type of application. So gravity inversion results is significantly improved by addition of small number of gravity data. Because now we have airborne gravity data, we have sparse gravity data, and we have airborne gravity gradiometry data. So it behooves us to put all this together, understand which data set contains what information, and how the interaction of the information in different data sets occurs. So that's really what's going on here. So last part is a bit of my pet peeve right now. I've been an inversionist forever, and I used to say that have computer will travel. For people who like American cowboy movies, it's equivalent of have gun will travel. I should say have computer will invert. It's like equivalent of cowboys have gun will travel. Until a few years ago, I realized that's such a wrong approach. What we really need is to go beyond geophysical images, or geophysical result, go into a statement about geology. So this is one part that, again, this is CC, Sarisha Martinez's work as part of her thesis. So we go back to the iron ore exploration in Minas Gerais region. And we looked at gravity gradiometry data earlier, that's first case. It so happens in this case, at the same platform, they acquired the total field magnetic data. Now we can invert magnetic data. In this case, what's interesting, hematite is highly high density, but hardly any magnetic property, so low magnetic susceptibility. Other rock units in this area would have lower density, but some moderate noticeable susceptibility. So those contrasts between the physical properties gives us a basis for doing the geologic differentiation. In this case, CC was able to actually do one step further, get to the lithology characterization stage. So what we've done is two approaches, totally independent. One is you take the standard generic physical property table, you have ranges. Then you look at the cross plot of recovered susceptibility and the density. You add density to the background. Then you get to absolute density. Then you just use the range to partition. This gives you the hematite, others the corresponding rock units in this area. That gives you one result. So this is again the hematite, where other units, but some of this high density part is removed because it has noticeable susceptibility, so cannot be treated as hematite. However, you can do this independently because we have one geological cross-section. How much time do I have? About 4 minutes, I suppose. Yeah, good. So, okay, thanks. So we have a geologic cross-section obtained from drill hole information, and we know what each rock unit would be. And we have, in this case, a cross-section cut out of the 3D density model, and same cross-section cut of the 3D magnetic susceptibility model from the inversion. Now what we can do is something that the remote sensing community has been doing as a routine, namely using the end-member approach. So in this case, we have now the data, which is model recovered from inversion. Then we have an approximate representation of geological truth. Therefore, we can establish mapping between the unit and the combination or cross plot of the physical property. And so this is how Sarisha did this. You take the geological cross-section, you discretize them according to the model discretization we used in the inversion for the airborne gravity, gradiometry data, and magnetic data. Then you have a corresponding value recovered from inversion. From this, you establish a mapping. That's shown here. So basically, you have, again, that's not quite the same as the generical table we pulled out of textbook, but amazingly, this partitioning is highly consistent with what the generic physical property table gives you. You go ahead and use this to do the geology differentiation, identify different lithologic units. So that's geology, that's density section, that's susceptibility section, that's result of geology differentiation. You notice this pink region corresponds to the soft hematites, the highest density region. The other part of the blue corresponds to the etaborite in this region. So it's very consistent. Of course, this is applied to, you take the end-member analysis, one cross-section, you apply that mapping to the entire 3D model, then you get a 3D geology, in this case, a lithology. So in the end, we have 3 geology differentiation results. First is simple thresholding of density, gives you the most likely hematite region. Second is using generic physical property range, gives you not only the hematite distribution, but also representational proxy of the other lithologic unit. Then the third one is using the end-member processing, making use of the geologic cross-section that's right there in the study area. What you notice is in terms of hematite distribution, it's highly consistent, and as you go into this case, it has refinement. And also, these 2 independent geologic differentiation approach gives you very consistent result. So that consistent, we think, gives credence to this approach. And also, there is a 3D geological model that's produced from drill holes by Valley, which we believe the result here is consistent. So quick summary in this case is we're able to do quantitative integration of airborne gravity gradiometry and magnetic data. And we know the magnetic data right now is it's well developed, and its frequency content is wide enough for a lot of application. And so with this integration, we were able to do lithology characterization on the deposit scale. It's not just on the regional scale. And the consistent result from this approach was from 2 different independent approaches, actually, such that the result is, to some extent, reliable. What it means that the information content in the airborne gravity gradiometry data, that's what we're discussing here, is there's enough information to do work or quantitative work in the deposited scale for exploration purposes. So quick summary, we believe there is much more information in the airborne gravity gradiometry data than have been perceived by the community. The reasons that we show 3 cases with different application purposes that actually we can look at the detailed density distribution on deposited scale, not just on the regional map or structural delineation. So significant short wavelength information is actually indeed available for mineral exploration at deposit scale. I think that's quite significant. And the long wavelength signal can be supplemented by other means, namely the ground or airborne gravity data. And so as discussion going on with next generation gravity gradiometer and the improved processing, we hope to actually the community will actually be able to push the information spectral content towards lower or short wavelengths. That would be really exciting. So with that, I conclude my presentation. Thank you for your attention.
Thanks, Waljo. Our next speaker is Helen Gibson, and her topic is Constrained Stochastic Inversion of Gravity Gradients. Helen has worked in the geosciences innovation industry since the early 90s, first with GeoTrack International, who commercialised techniques for thermal history reconstructions for the oil and gas exploration industry. And later, in the last decade, Helen has been with Intrepid Geophysics, helping to grow better software tools for integrated geological and geophysical modelling. She enjoys trying to make science communication simpler to understand, and she is also a keen promoter of bringing geologists and geophysicists together. Thanks, Helen.
Thanks, Terry. It's all true. Oh, except I haven't got it. It's there?
Oh, sorry.
That's it. Gibson.
Oh, right.
Thank you. Sorry.
Is that your regular note?
for some reason.
That's fine.
Okay, that's good. Right. Sorry. Thank you for your attention. We'll get straight into it. So the outline of my talk today, it's going to cover four main topics. At first, I'm going to spend a bit of time to give an overview of the conventional scheme of performing joint litho-constrained stochastic inversions using conventional data. Just to set the scene, I think that's important. So this was something originally proposed in 2D in 1995 by Muscard and Tarantola. I'm going to dwell on the fact that having a close starting geological and property model is very important. So next we'll move into that scheme and being able to add gravity gradiometry data to the scheme, and discuss finessed approaches, and finally get to some outcomes and applications. So I think a good place to start this conversation is at the end point of a forward 3D modelling exercise. For example, you may have had a built model of geology, you may have loaded some rock properties, and you may have done a forward 3D calculation of responsive GZ, shown on the right. And if you have observed gravity, you can make a comparison with the observed to the modelled, and if you like what you see, you can say, I'm done, that was a good model, I'm finished. If not, if you want to improve the fit, you can iteratively go about making changes to geology geometry or properties. And if you want some help with that, you're heading into an automated process, as we know, inversion. So in this case, it's a decent fit, but we're going to think about improvements. We also happen to have two independent data sets. So I'm showing TMI on the right-hand side and the terrain-corrected scalar gravity on the left-hand side, where the signal is displayed in Z. These are gridded at 1/4 of the line spacing, so it's a more high-resolution TMI. So both of these, and I haven't said too much yet about this case study, it's the Merlin-Lee subbasin, it's the onshore equivalent of the Carnarvon. So both of these signals are quite well displaying the geology here. We can see a representation of the Merlin-Lee subbasin nicely, and we can also see some representation of the underlying crystalline basement of the rifted margin. So just to put the case study in its location, here up on the northwest shelf. As I said, it's the onshore equivalent of the Carnarvon Basin. It's fairly underexplored. But the process now is for the modeller to consider which units to put together in the right amount of simplicity to represent a good model. and they've focused on the Permian sequences, in this case because they're containing the cap, source and reservoir units of a potential petroleum system, not discovery. This is a regional sort of modelling exercise. So the other thing the modeller is doing, putting together a close starting model. We recommend to bring together diverse constraints as much as you have. Mapping, cross-sections, drill holes, seismic, gravity, EM. Bring it all together. The reason is, of course, it's as in the mapping data, you have good constraint on surface geology. Drilling gives you a good trace and high reliability in that zone. You're going to need to go to seismic and potential fields to fill out the bottom of the model space. So seismic, being a reflection technique, is particularly good at the vertical variations and layering. Potential fields is good at picking the edges and the lateral changes. Another thing as a modeller you may want to do is some innovative processing, so that, for instance, what was done here is a Murty and Rao depth to basement estimation on the left, and multi-scale edge detection on the right, picking the worms for the purpose of fault network generation in the absence of very much seismic data. There's only 5 lines in this region, and this region of the model is 160 kilometres or so in north-south. So what they've done is to bring together as much information as they can for their a priori geologic information. This one's built in an environment which includes the digital elevation model and also was able to handle variable data sources in rich and sparse data combinations. And the model is geolocated in a real-world coordinate system. This is important because when you're going to be loading the grids of TMI and gravity, you need the software to handle them in a native way. And for instance, you then have access to things like an IGRF calculator, and all you need to do is dial in the date of the survey. So our purpose for performing a joint litho-constrained stochastic inversion, we wanted to improve the fit of the forward responses, and we're doing it by an inversion scheme to infer something about geology geometries and rock properties. This is what we're going to do. So you may have seen this scheme before. It's a well-used diagram, but what it's showing is the modelling spaces for 3 independent data sets, being geology in green, and all the models supported by magnetic observations in red, and those supported by gravity in blue. So when we begin with our starting model out here in green space, you can imagine it hasn't yet been referred to the geophysics. So once the inversion process begins, we drive down the misfit and we're driving closer to the convergence into the overlap zone. But we don't stop there. Because we're performing a Bayesian approach, we're going to continue to perform inversion and gather all the models that are consistent with the 3 data sets. And therefore, at the end, we may have millions of models, and we're ready to perform a likelihood statistics on those models. Here's a plot of the misfit evolution for the Merlin-Lee. The number of iterations is 8 million. So up on the left-hand side, it's the beginning point before we really start to drive the misfit down by referring to the geophysics. At some point, you're going to level off into the converged zone, and we'll keep the models from that point onwards. Just to give a bit of a flow chart here of the Markov chain Monte Carlo inversion scheme employed. What happens in the beginning, of course, we're loading the geological and the property models. Then we're proposing a change to a single voxel of the previous model. And so the cartoon is just picking on one cell at a time. In this case of geology, it chooses a frontier cell and it changes its geology identity, possibly to the Lions group in the darker blue. Next is that we need to check, is that a suitable geological change to make? Is that reasonable? So I'm skipping over the subloop there because I'm going to explain that next. So what we do, if it is suitable, we proceed into a forward model computation and compare the observed with the modelled, and then and then assess the likelihood misfit. If it's if it's improved, we keep the model. If it's not, we throw it out, although we very occasionally keep those as well, and that's another mathematical conversation. To explain the subloop, we're going to here run a series of tests for geology geometry. The user is able to set up rules or tests, and these are the ones that happen in order. So for instance, if the new proposed model touches a fixed cell, that won't be allowed. And a fixed cell is something which is surrounding a drill hole or on surface where the user has set it to not change. Another thing is to preserve the Younging order. So for instance, if the change means that the stratigraphic order goes out of order, for example, the geological story here is that if you have basement thrusting over tertiary sequences, that would not be allowed, and as a user you can set that to never happen. So another rule. The other things are more about, well, their commonality, volume ratio and shape ratio, and each of these are set up by an exponential probability law. Commonality is about retaining the original shape in terms of overlap compared to the starting model, and likewise the other tests talk about the changing geometry. So property models, these are also explored during inversion, and how we set those up can be by a lookup table on a per lithology basis, and we set a normal or a log normal property law, whatever is appropriate. Alternatively, you can commence the inversion from a VOXI set, which is either custom made or it could be the result of a property optimization run. Alternatively as well, you could perform a kriging exercise if you have drill hole data, and then proceed to perhaps fill in the spaces which are unknown with random values defined by property laws. So how the perturbation happens in the inversion scheme is, again, a cell is selected at random, and a new property value is selected at random, and what's allowed is within 2 standard deviations about the mean. Just to sum up this conventional scheme, we start by building a model for property and geology. We set the resolution, we set the constraints for geology geometry and property. We set the ratio. So for instance, you can have a fixed geology inversion or a fixed property inversion or any ratio in between, say 50-50 or as you wish. And of course the grids are prepared and the precisions are set. Just to finish off this case study of the Merlin-Lee, here down the bottom right hand, so we have the final grids at the end of inversion. And you can see by the misfit plots on the furthest on the right, they're nice bland colours, meaning that we've achieved a good convergence of the solution. So here is the most probable density distribution, synthesised or on the basis of the final 3 million models which were accepted. Likewise in geology, here is the most probable geology represented. We're focusing to show the Lyons group. In this case, you know, it's useful because you can compare this posterior model with the starting model and analyse the depth and spatial volume of this Lyons group, and it's a key factor for a petroleum system. So these are really useful results. So you can extend, and we have already implemented extension of this conventional inversion scheme to now accommodate airborne gravity gradients. We recommend the use of the complete tensor and the component tensors, and likewise from Falcon, the components are NE and UV. So you can choose, in this joint inversion, you can choose the full tensor or any number of components, and luckily this process is multi-threaded, so throw it at a supercomputer, see how long it takes then, because it will be computationally expensive. Here's a plot, a typical misfit evolution for all components. So you can see that each component plateaus at different levels, and this is reflecting the different survey noise levels. Notice that GZZ, in light blue, is noisier than any of the others. And notice that the best channel is as GXY. So the implication of this is that the full tensor constrains horizontal features better than vertical features. And we know this by comparing the potential field versus the seismic data from my earlier cartoon. And so therefore there's more uncertainty in the vertical. So what we need to do in our inversion scheme is driven from 2D grids. And so when we're dealing with airborne gravity gradiometry data, it's important to avoid adopting errors. So what we recommend is only to use properly QC'd data, to use, of the delivered products, use the one closest to the measured signal as possible, and take care with gridding. So employing a true tensor gridding algorithm, for example SLURP and its variant in Falcon, so to achieve grids which aren't over-smoothed and which preserve the raw signal. You obviously need software to be able to handle that type of demand, and here there's 2D, 3D and table views linked, which I'm showing. And so in the 3D view on the top right, we're looking here at eigenvectors, and these are obeying the right-hand rule and the sign of the gradients, both honoured in this view, and that's important. So which part of our geological model will airborne gravity gradiometry data most inform us about? So the tensor data is typically, the sources are relatively shallow, so, and conventional is typically rather deeper in comparison. So herein lies our challenge. Should we be doing inversion on the free air or the bouguet? And before I answer that question, we're going to divert onto two subtopics. The first subtopic is to talk about traditional soil rock mechanics, which hinge on the role of pore pressures. So gravity loading compacts pore space, and hence density increases with depth. And in extreme topography, this turns into a 3D problem. So being concerned about compaction is paramount, because airborne gravity gradiometry data are exactly responding to this, the density contrast at high precision. And also the typical source depths are shallow, as we said, less than a kilometre, and this is including the weathering zones. And so what's recommended and in fact implemented now is to set a depth density function in your starting property model. And the scheme should obey this function in combination with the probability distribution function set per lithology. And we suggest this way, which is an adaptive reselection of the mean with depth. So the second subtopic, I'm referring to Matt Zengera's work for Anadarko, where the study was on the Wattenberg Basin in Colorado about reprocessing of Bell FTG data. So Matt investigated the impact of the terrain correction and the effect it had on when there were variable densities in the surface. So he applied a sophisticated approach to correlate the digital elevation model with measured and processed full tensor data to arrive at a point density estimates on surface. And these were propagated down into a model which he called the seeding model, and then following that, following inversion, he arrived at an optimised 3D density VOXI set. So a very sophisticated and challenging workflow. So here I arrive at the answer or the recommendation. And so if you're using Bouguer data, then be very concerned about how the terrain correction is performed, because conventional use of a single mean density is just not going to be good enough. Using free air is actually probably recommended. If so, use a high resolution DTM or bathymetry in your geology and property models. So another way to improve the realistic nature of the near surface geology and properties is to perform a high integrity approach inversion of airborne EM. This helps a lot, and if you're able to combine it into an integrated data modelling environment to build your 3D geology even better. So an outcome of this work, which is now very real, Jared Dunn is going to be speaking on it at ASEG in the next coming days. He's going to speak about the problems of constructing shallow velocity models adjacent to submarine canyons on the northwest shelf, where GZ can vary by up to 30 milligauss due to the extreme bathymetry. And these effects are even stronger in the airborne gravity gradients. So, through a litho-constrained stochastic inversion, this sensitivity, we suggest, can be tapped into for deriving very useful posterior probability density VOXETs. And they can inform much better velocity models, and in turn you can achieve improved 3D seismic imaging in petroleum settings. So I commend that talk to you. In conclusion, to say again, you should take care and use only properly QC'd airborne gravity gradiometry data. And in fact, the scheme can show up problems in poorly QC'd data because the physics of the signal should be honoured consistently, i.e. hang together, in both the full and the component states. So use free air is our recommendation in combination with a high resolution digital terrain model or bathymetry, and or otherwise use Bouguer and face the challenges of doing the terrain correction very well. A good starting model details near-surface geology and properties very well. So, for example, honouring soil compaction laws and using airborne EM inversion, which is going to pick up really well the weathered surface, the channels, the prograding sequences. As I say, use all the data you've got. So airborne gravity gradiometry data can also provide posterior density models to better inform velocity models. I think this is a really valuable use and hence contribute to improved 3D seismic interpretation, particularly deeper imaging of reservoir rocks and economic zones. So that's really all I'd like to say, other than to acknowledge and thank very much Richard Lane for early mentoring of the Litho-Constrained Stochastic Inversion scheme as implemented in GeoModeler. Jared Dunn and David Walraven for permission to speak about the background to their case studies. Thank you.
Thanks, Helen. The next speaker this session is Ian Macleod, and his title is The VOXI Approach to Modelling 3D Density and MAG Properties of the the Bob Smith Test Range. Ian is a founder of Geosoft, where he is currently Chairman and Chief Technologist. 40 years ago, he began his career with a gravity meter, which led to a position with Patterson, Grant and Wasson in Toronto, where he worked on interpreting geology from gravity and MAG data. This included developing the first popular geophysical inversion programs, MagMod and GramMod. Together with his co-authors Robert Ellis and Taranish Pithawala, Ian continues to work on multi-physics 3D inversion developments at Geosoft. Today he will show us these developments applied to the R.J. Smith test range. And I'll try and get this.
great. Thanks, Terry. Yeah, thanks very much, and thank you very much for the committee for organizing this, and Theo for making room on the agenda for me. I'm really happy to be here. Yeah, as Terry said, we're going to be talking about inversion, which we've been seeing a lot of today. Some of the conclusions I'm going to come to may differ from what you've seen, which I think is good and healthy, since we're talking about the state of the art today. Now, one of the important acknowledgements I want to make is my co-author, Robert Ellis, who isn't at the conference, so I'm here to give this talk. But 2010 was the last conference on airborne gravity, and Rob Ellis joined us towards the end of 2010. So this is a good point in time for us to talk about what we've been able to accomplish with Rob over the last 6 years. Now, when Rob joined Geosoft, he came from BHP, and formerly Rob and Yaoguo Li were founders of the geophysical inversion facility at UBC. And really it's that work that Yaoguo and you and Rob and that whole team you had there that's led to what's become ubiquitous now. And I hope you take tremendous pride in this 3D inversion that, as you said, is quite ubiquitous now. But when Rob joined us, I said, look, Rob, you've learned a lot in the last 15 years. And I want to take all that you've learned in 15 years and let's start again using modern computer scientists, which we have at Geosoft, modern thinking, and here's your chance to build a system for the future and have an impact on broader exploration, which is what we serve. And so we started with that energy in 2010, and you're going to see some of that today. So now in this talk, I am going to talk about 3D inversions, and we will just get right into it. I have focused on the R.J. Smith test range, which Theo asked us to have a look at. Now that test range has a number of very good data sets. The TMI data, it has ground gravity, which you've already seen. It has Sanders airborne gravity, the Falcon GZZ and Falcon AGG data. And the site is located, I need some help here. There we go. The site is located about 130 kilometers east of Perth, and Des, there is a geology map. It's called the Yilgarn. On the map of Australia, it's brown, and so that's what we know. But once you know it's a Yilgarn, you know a few things. You know it's going to have quite variable densities. You know the densities are going to range plus or minus 0.3 grams per cc. You know there's going to be a lot of magnetic things and unmagnetic things. It's typical Archean terrain, and welcome to exploration. Often that's all we know. We got some ground, we got some cool anomalies, and we got to start from somewhere. So I think the R.J. Smith is a good one that represents a pretty typical case we have. Now what we're going to do in this talk is first of all look at terrain modeling. I'm going to touch a little bit on sampling, thinking about how we address survey height and model cell size. All three of these things work together. I'm going to compare inversions. We're going to invert the ground gravity, the airborne gravity, and the airborne GZZ. And we're going to actually look at a practical comparison of inverting GZZ data with full AGG tensor data. And I'm going to look at susceptibility and MVI from TMI for this data set, and then we're going to do a joint inversion, or joint, what we call cooperative susceptibility density inversion. So VOXI inversion is your standard Tikhonov regularization, all those fancy words. It converts geophysics into useful 3D physical property models. The reason I say useful, it's the box quote that all models are wrong, but some models are useful. And the plasticity of the potential field problem especially leads to understanding there's many possible distributions of physical properties that will explain exactly the same potential field. So there isn't one answer, there's many answers. And what we're striving to do is come up with something that's useful. Now in VOXI, over the 6 years, we've developed quite a few particular features that help make it useful. We have MVI susceptibility, which models the magnetic vector intensity and direction. Gravity gradiometry that you're going to see today. We're about to release IP resistivity modeling. We have EM, frequency domain EM inversion. I'm going to talk a little bit about the Cartesian cut cell method, which is critically important for terrain corrections and IRI focusing. Now one of the most important things I think about VOXI is the fact that we run the inversion on a high performance computing cloud environment. And that lets us do a couple things. One is it lets us run really big inversions in a reasonable amount of time. But for me, even more important is that it can run inversions fast. So reasonably sized inversions, 300 by 300, we can get an answer very quickly. And the big benefit of that is we can iterate. And you're going to see some of the benefits of iteration in the presentation today. In fact, all the modeling in this talk I did in my evening time over a period of about a week. So that this is an example of what a geophysicist, a mere mortal geophysicist like me, can accomplish in about a week. Now when I say mere mortal, you will see no math in any of my presentations. I leave Rob to do all the math stuff. I'm the more practical, mere mortal guy that's trying to make this stuff work for all of you. So, terrain modeling with Cartesian cut cell. Now, gravity, of course, is sensitive to density contrast. The biggest density contrast is between the air and the ground. And compounding that problem is that air-ground density contrast is really close to the measurement platform. So you've got a closeness problem and you've got this very large density problem. So critical is getting a really good terrain model removed from your data so that you can begin on the modeling. Now one of the challenges with voxel style approaches to modeling is that we have to slice the voxel into flat horizontal layers. And then that causes these ridges. And then for the terrain problem in particular, you end up having these terraces in your model. And so that's a real practical problem both for getting terrain out, or when you get to modeling, if you have density contrasts that are at the surface, you're going to see these terraces in your density contrast. So what we've introduced is called the Cartesian cut cell method, and what we do is we take each of the cells and we just cut it by the terrain and effectively produce a smooth terrain model. And then in the inversion and in forward modeling, you'll end up with effectively a clean model response. And that's critical, especially with AGG modeling, and if you have any terrain whatsoever. So let's look at the gravity terrain at the R.J. Smith. On the left is the terrain model. You've seen it in other slides already. One thing I will want to point out is you can see an edge here and an edge here where beyond the edge it's a little bit stippled. So one of the things you need to do with modeling is get really good terrain within your model area, but you've also got to extend it out to cover the size of your model so you can pull off the other terrain. So what we do, and what most people will do, is they'll stitch in the SRTM data. And for GeoSoft users out there, I would like to say that we now have the 30-meter SRTM data available on the DAP server for the entire world. So you can pull down 30-meter data, and that's what I have here. So you can see the slightly higher error here, but it's outside the survey area, so that's perfectly fine for terrain corrections. Now on the right, you can see what the gravity field is for GZZ for this area before terrain correction. So this is what you would have seen off the aircraft. The model, the actual terrain I have in here is modeled, and I've added it to the GZZ given to us by Falcon to make it look like that. When you subtract the terrain correction, you will get that, which you've seen in other slides as well. And the dynamic range, the dynamic range of the gravity went from minus 60 at VOS to plus 190, and after terrain correction it goes from minus 30 to plus 74. So you can see that most of that field is terrain. So critical to get that right. I have coincidentally picked, I think, the same profile that the VK1 had picked. And it's right across that little hill. It's right in the middle of this area. And clearly we know from looking at that Yilgarn great geology that there is a feature going through here, and it's probably outcropping here. Now that's what the hill looks like. It's about a 50-meter hill. It produces a 250 at VOS GZZ anomaly. And here we're looking at what the model response we get for different resolutions of the cell size. Our reference is 5 meters, and then as we go to 50 meters, we can see that we're underestimating that terrain correction. Here is the error. Again, using 5 meters as a reference. We find that the 10-meter cell size is virtually the same as 5 meters. So our conclusion from that, you don't, for terrain corrections, you don't need to go any smaller than 10 meters if you're using Cartesian cut cell. And then each of these lines is stepping out to larger and larger cell sizes. At 50 meters, we can see the amplitude here is about 25 ETVOS, maybe 30 ETVOS, with a density contrast of 2.67. So a couple of things you can conclude from that. One is that 50 meters is much too coarse for doing a useful terrain correction. And secondly, you can conclude that for modeling, however, after I've removed the terrain, I could expect this to be an order of magnitude smaller in terms of the error I'm introducing into the modeling. So for modeling then, we're dealing with perhaps a 2 to 3 ETVOS error introduced because if I'm going to use a 50 meter cell size. So something to think about when for any given model area. Quick one on the data coverage. We have 3 main data sets we're working with. The ground data, which you've already seen. It ranges in sampling from 50 meters on, actually it might even be 25 meters. Is that?
50 by 50.
Yeah, it's 50 by 50 in here, out to 100 meter lines, 250. And then in the background here, it's about 500 meters. The Sanders was flown north 30 degrees west on 50 meter lines at a 95 meter flying height, based on the data I got. Louise, I see you squinting. Oh, well, the average in the database says 95. They may have paid for 80, but they got 95. And the Falcon AGG was north 60 degrees west. And so all the data sets are just a little bit different, well, with the ground a lot different. This is what the data actually looks like. Now note that I've rotated it, so north is this way, so I've rotated it to get the maximum screen real estate here. So there's the nice ground feature. The Sanders has done actually a remarkably good job of picking this up, and the Falcon GZZ has also picked it up very well at and as you can expect, much higher frequency information that we can see in that. All right, let's look at the model responses. I'm only going to show you this once. When you run inversions with systems like this, you set the noise level, and as long as the inversion completes, you're going to get the data that you asked it to fit. And that's one of the beauties of potential fields, is it will fit your data. And the model response, depending on my noise, will always look exactly the same as what I've given it. And the important point here is I don't need to show you any more model responses because they always look like the data that I put in, depending on the noise level I put in. They always fit, but the models can be quite different. So. Now one of the differences here, you will see that with the, each of these, they're fitting exactly. I'm only showing the GNE for the Falcon, but you'll see that the model response is quite a bit smoother. So one thing to note here is that in this case, we're actually using the inversion code to do the filtering of the data. In these other cases, the contractors or whatever pre-processing had filtered the data for us, and so now we can model to exactly the data that was filtered. But when you invert directly for GNE and GUV, which we can in VOXI, then you actually increase the noise to what is actually the noise of the data, and the modeling effectively does the filtering for you. Okay. So let's look at some spatial considerations. Now, what we wanted to do was look at what's the difference between modeling at 50 meters and 25 meters and at different elevations. And in my own experience, what you want to get is to the right height above the model that you're looking at with the right cell size that is that you're collecting in the data and is useful for the geology I'm trying to pull off here. So here's the Falcon GZZ modeled at as it was collected. Well, it wasn't collected, it was calculated, but from a 65 meter clearance on a 25 meter voxel cell. And so this is really our reference. And now I'm giving you density depth slices with quite a different color scale. And so here's our high density feature going through here. And this is at the 100 meter depth, and you can just see some of the detail approaching the noise. And then I've dropped down to the 500 meter depth here, so you can see that it gets quite smoother with depth. Pretty predictable. Now, let's upward continue to 100 meters. And one of the reasons I'm going up to 100 meters is I want to increase my cell size to 50 meters. And at 50 meters, I can run many more inversions in the same amount of time. And am I losing anything if I do that? And my conclusion from this is I'm not. I'm actually getting pretty much the same basic information that I was getting at 25 meters. At 500 meters, certainly it's the same. And it's a very subtle difference in my actual data. So from this I can conclude I can comfortably model at 50 meters and not really lose anything with this particular data. Another big question we want to answer is, do you want to model GZZ, which is provided with the Falcon data, or most of the contractors will provide GZZ, or do you want to model the full tensor, the 4 components, the GUV, GNE from the 2 instruments, which we can do as well. So I wanted to compare that and do a shoot-off. Now I must say that Rob and I had a disagreement in this one. Rob said, yeah, absolutely, model the real data. And I felt, well, that's a lot of effort. Let's model the GZZ and let's actually have a shoot-off and compare. So here's the results of that test. So here's the same data I was showing before, and here's what we get when we model the GNE, GUV to 100 meters and to 500 meters. Now they're different, and there's a couple of points to make here. I went ahead and did this, and I probably ran 3 or 4 models to get this one that I was happy with. With this one, I spent 2 days trying to get this result. And here, I guess Geosoft has failed you in that I couldn't figure out how to get it to give me a result. And Rob said, oh, you got the noise level wrong, you got this wrong, you got that wrong. Let me do it. So he took it away. And he spent a day, and he produced this model, and then educated me on the things that I had done wrong, and that was fine, and produced this. And we both agreed that, well, you know what? We actually feel this one's better in this case. And now we're spending time looking at this model and how could we improve it. Well, one of the obvious things is reduce the noise level so we can start to pull out more of the detail in this model to get it to there. But that would have taken us another day. So at that point, my time was running out, I had deadlines, and I said, well, let's just leave it. Now this is pretty typical for an exploration scenario. You got deadlines, you got to get stuff done. So this ability to model this one quickly compared to the slow iteration times for this one, in this case, we said it wasn't worth it. So we think we could have made this better, but we would have had to take a couple more days to have a couple more cracks at it. The other thing I want to point out is we are seeing in this particular version a bit of a challenge here, and here, these 2 highs at the deeper level. You can see some of the power in that anomaly in the G and E, G and V is being pushed to something larger at depth. These are at the corners. We think this is a bit of an edge effect. So something else you got to keep your eyes open to when you're doing these inversions is watch out for these kinds of artifacts and side effects. You can't believe everything you see. It does fit the data, but you got to question where these things are coming from. Especially when none of my other models had anything significant going on in these areas. Computing resource, inversion time. So to give you an idea, the GNE, GUV data was 25 meters. And by the way, it has to be 25 meters because the detail of the data, we've got to model it as provided us at the 65 meter flying height, and at 65 meters we've got to go down to 25 meters in the model to properly model it. It was 4.5 million cells. We used 128 cores, and it took 125 minutes once the cluster was set up and running. So that's 2 hours and a bit. Now I'm used to running inversions in 10-20 minutes, so when I had to wait 2.5 hours, I lose my patience. GZZ, when we run at 25 meters, also 4.5 million cells with 128 cores is only 25 minutes, which is workable. But the real winner for us is GZZ at 50 meters, 700,000 cells with only required 32 cores, and I could get those in 12 minutes. So it's a lot less computing power and a lot faster, and that means I could run a lot more of them, which is important. So that was the winner for us in this shoot-off in the R.J. Smith. Now, Rob will say, be very careful that you say in this case, because in other cases it may be something different. It might be worth the extra effort to model the full tensor. And now let's compare it to a straight inversion comparison of the 3 methods. The GZZ, now what I've done is I've upper continued everything to 100 meters. So I've got everything on the same terrain clearance. I've calculated GZZ from the ground data, GZZ from Sanders, and taken the GZZ that was calculated by the Falcon folks in the Falcon data. And here are the inversions for comparison. It's actually really good. This is the ground data, and this is the Falcon GZZ data. And Yaoguo, this differs a little bit from your result. I question how they did their first inversion, but we got pretty well exactly the same from the Falcon GZZ that we got from the ground data, and that's just taking the GZZ as given to us, so straight in. And ditto, even at depth, this duplicates at depth. The ground gives us a little bit more character because it's got better resolving ability at that longer depth. And then you look at the Falcon. Predictably, Falcon is, because of the filtering required to pull the signal out, can't get the detail at the 100-meter elevation slice. But as you go deeper, it starts to bring up a credible response. I think some of these things are really filtering artifacts because of the wavelengths of the filter. But certainly the main feature here is coming up. And I was quite impressed that I could actually get that out of the Sanders system. I apologize for the color scale. I threw this in on the flight over here. It's on the poster outside. But this is kind of what you were doing, Yaoguo. What we do is we invert the ground data, actually GZ, and then we take the ground data inversion and we put it in as the reference model for a gradiometer inversion. And we call that the GGG method, which is on the poster out there. And what that does is it gives us the higher resolution that we're getting from the gravity gradiometer near surface, and we're getting the longer wavelengths from the reference model that we get from the ground. So it kind of does the same thing with just with a different approach. And so that's what it looks like at 150 meters, and this is only 150 meters below the ground compared to 500, but it's what I had on the plane to stick in there. But I just thought I'd show it for reference. Now let's switch to magnetic susceptibility. Since we've introduced MVI, that's become a really strong method of inverting for the magnetic field, and that's where we allow the magnetic vector to vary. And people ask, well, why would I do induced susceptibility? Can I just run MVI? And it turns out, well, the reality is induced susceptibility is in fact a more constrained inversion. So if you know that you have a magnetization by induction only, you're going to get more data from a susceptibility inversion. If you suspect that the magnetization vector is rotated, then you're going to get a better result from MVI. So one of the first tests to do is ask yourself, do I have a rotated magnetization vector? And the easy test for that is to run them both. If they're both giving you basically the same answer, that the main feature, by the way, these are shells. Now I'm looking straight down. These aren't slices. If they're both giving you basically the same answer, you can conclude that I'm likely mostly dealing with magnetization aligned with the Earth's field. And in that case, we would say, well, then go with the susceptibility inversion. In old Archean rock like the Yilgarn, that's not surprising. It's less, you less often have a problem with a rotated magnetization field. So in this case, we would say induced susceptibility is better. Here I have them both combined, and you can see they line up pretty well. By the way, in the bottom, I'm just showing these at an oblique angle. So we're kind of looking from up here down that way, and you can see the field, and here you can see the anomaly. Oops. Am I out of time, Terry?
Getting close.
Okay. So second last slide. So now with cooperative inversion, what we do is we do an inversion in one method, and then we take that inversion and we feed it into another method, and we use that inversion to control the weighting function while it runs the inversion. And we're effectively saying, when we run the density, take your susceptibility model and use that to weight it to make it look in shape as much as you can like the magnetization susceptibility. And in that way, we're saying you are cooperating. It doesn't imply a hard connection. It just says, well, make it have the same shape. So the effect here is when I run a density inversion by itself, you can see this is pretty much what John showed as well. This is the shallow part here and here, and you can see this little keel running underneath. The susceptibility doesn't really have a keel there. It has two features in either case. So when I say take this and fit the density to cooperate with the susceptibility, it effectively has removed that keel and given us a shallow bit there, and then split the shallow bit into two, etc. Remember, all models are wrong, but some of them are useful. So it might be that this is a little bit more useful in this case. I mean, if I was drilling a hole, I wouldn't be trying to drill that keel, for example, because it's deeper and it's riskier. So doing inversions like this might help us reduce the thinking of this. The other point I think I'd like you to take away from this is that this is a result of running lots of inversions because I could run them fast. And I think this is one of the advances since 2010. It took so long to run inversions that by the time you got an answer, you go, okay, great, I'm done. Let's work with that. Now you need to go back at it, change my noise level, introduce constraints, look at this, look at that, do some cooperative inversion. And through that, you're engaging the interpreter's mind to think about it, combine it with the geology, and come up with a better feeling for exactly what's going on. So to conclude, with Cartesian cut cell, a 10-meter cell size in this case is sufficient for terrain, 50 meters for inversion. We found 50-meter model cell was ideal for this data with 100-meter elevation. In this case, GZZ produces an equivalent or better inversion than GNE, GUV. There's no evidence of remnants based on, or magnetization not aligned with the Earth's field, based on comparing MVI to susceptibility. And you saw the joint cooperative inversion, we feel made a more consistent model. And our ability to run many inversions quickly lets us explore the range of possibilities, which leads to a better understanding of the limits of the physical property model. Thank you.
Thanks, Ian. The next presentation is by Airborne, Christensen, and the title is Mapping Gravity over Inhospitable Terrain. Airborne is the owner of Nordic Geoscience Proprietary Limited, consulting worldwide on ground and airborne geophysics. Working for BHP Billiton in the late 1990s, Airborne was actively involved in the initial development and deployment of the Falcon Airborne Gravity Gradiometer. He was working on minerals and petroleum exploration projects in Australia, Asia, Africa and the Americas, and has managed research teams and technology companies. His areas of interest are geophysical technology development and deployment, potential fields, and the integrated interp of geophysical data for minerals and petroleum exploration. Has an MSc in geophysics from the University of Aarhus in Denmark and a PhD in geophysics from the Colorado School of Mines. He is a member of EAGE, SEG and ASEG. Airborne is based in Melbourne, Australia. Okay, how do you get out of this? Go click. Escape. And we go there. And there's that one. F5. Done.
Thanks very much, Terry. And thanks very much for giving me the opportunity to talk to you today. I think it's fantastic that the organizers have been able to pull this off at this time in downturn of the industry. And I look out here and I see pretty much everyone, there is everyone. I feel a little bit like you know, Michael Corleone at the meeting of the Seven Families. But don't worry, I haven't taped a gun to the toilet out there, so it's all good. So today we're going to talk about mapping gravity over inhospitable terrains. And so I'll start out with just a brief introduction of, you know, why would you ever want to do airborne geophysics in inhospitable terrains. And then we're going to look at some of the specific environmental factors that affect you when you operate in these regions. So we're going to talk about the polar regions, the deserts, the mountains, the jungles and offshore. But I also want to tell you that one of the sort of common themes that come across in all these inhospitable areas is actually logistics. That it's the very remoteness of these areas that often is one of the biggest challenges when you operate there. So, if you have a well-executed airborne or airborne gravity gradiometry survey over any given exploration tenement, then you can typically do that in a period of maybe a few weeks up to a few months. But you contrast this with trying to do that with a ground geophysical survey, and you're looking at a much later time, much larger time frame, maybe months up to even years. And that prolonged exposure to field personnel is is naturally an increased exposure to health and safety risks that's particular to that particular environment. So the reduction in safety risk that's coupled with a timely data delivery, that's really what makes airborne geophysics such an attractive proposition for your explorer. Now, airborne gravity surveys, they've been flown over all continents of the Earth, including the Antarctica. Airborne gravity gradiometry, they're just behind. They've been flown on 6 continents of the Earth, in over 50 countries, and I think by now, Dan, you have to correct me if I'm wrong, I think we have more than 4 million line kilometers that's been flown to date. So many of these airborne gravity and gravity gradiometry surveys that have been flown to date, they've been flown over inhospitable terrains. I mean, one of the primary reasons for flying airborne surveys as opposed to conducting a ground survey is the very fact that the survey area is either inaccessible, in a hostile environment, remote, or all of the above. So in the past few decades, airborne gravity and airborne gravity gradiometry, that's been flown on all continents, ranging from the Arctic to the hottest deserts and over the highest mountains. And so in this presentation, we're just going to have a look at some of these specific changes that are, some of these specific challenges that are associated with these areas. So let's start and have a look at the polar regions. If there are two words that describe the polar regions, that is that they are cold and remote. And so that produces some very particular challenges. And the first environmental challenge that you have is the temperatures. And so the temperatures encountered in polar regions are the key environmental challenge. Okay, as equipment such as computers, sensors, etc., may not operate well in extreme cold. Okay. And it's especially the installation and maintenance of semi-permanent instrumentation, such as base stations, reference base stations, GPS antennas, turns out to be especially problematic in these areas. Another things to consider is that the polar regions are cold. And so repair and maintenance work on survey aircraft is difficult if hangars are not available. And it turns out, of course, that if hangars are available, they can often be prohibitively expensive. The polar regions, of course, are sparsely populated. And so finding a suitable base within a reasonable distance of a survey area, that can often be a problem. If you happen to find such a base, you will find that, if you find that suitable, it can be challenging. Okay. If you find such a base, then you find that the infrastructure is limited. Okay. And so getting fuel to the area can be both difficult and expensive. So for all polar surveys, extensive planning is required. Okay. You'll also find that you will have problems with reliable power. Okay. And that brings you to the issue that you might have to bring in portable generators. And that opens up this whole Pandora's box of having to refuel, having to reliability and what have you. And the problem especially with airborne gravity and gravity gradiometry is that they have to be temperature controlled all the time. And you lose power for a very, very short time, and you're looking at significant delays in getting the temperature control back online. But despite these challenges, large airborne gravity and gravity gradiometry surveys have been flown in polar regions from the far north to the Antarctic. However, of course, when you operate in polar regions, you have to steel yourself to the fact that there can be periods of extreme cold that can curtail airborne operations just simply due to safety concerns. But it's not all bad in the polar regions. You have the polar summer months, and they do provide a 4 to 5 month window where you have near to 24-hour operational envelope. It's not bad. That is, if the weather permits. Now, enough about the polar regions, and let's have a look at the specific challenges that face you when you're working in the deserts. Okay. If there are two words that describe the deserts, it is that they are hot and they're dusty. So the first environmental challenge that you have when you operate in desert area is typical high heat. And that brings about issues as cooling down the electronic equipment. Okay. Also, you'll find that the heat generates turbulence, which affects the quality of the airborne gravity and the gravity gradiometry data that you're trying to acquire. Of course, you may find yourself in periods where there's such extreme turbulence that you're not able to fly at all due to safety concerns. The second environmental challenge that you have in desert is the dust. And the dust has a tendency to come in everywhere. Okay. The AGG systems that I've seen in operations, the one that takes the hardest battering are the ones that operate in desert areas. And it's due to dust coming in bloody everywhere. So the prevention of influx of dust is absolutely paramount and required. And pity the poor geophysicist that is stuck in that environment for a long period of time. The logistical challenges that you find in desert region, they're quite akin to the challenges that you find in polar regions. Both areas have limited infrastructure, and so finding a suitable base is an issue. Likewise, sourcing fuel is both difficult and expensive, so planning is required. And you have the same issue as before with portable generators and all the problem that entails. Now let's have a look at the challenges that face you when you venture into the mountains. And the challenge in the mountains is to fly draped surveys at a nominal terrain clearance. All airborne gravity gradiometry systems and some airborne gravity surveys are nowadays flown in a smooth drape over the survey area topography at a nominal terrain clearance. And the nominal survey terrain clearance, that's a function of the chosen line spacing, the expected target depth, and of course is always subject to flight safety considerations. The challenge of flying a draped survey is twofold. You want to drape the survey tight enough that you honor the nominal terrain clearance that you have in the contract. At the same time, you want to have a survey that's draped loose enough that you avoid excessive aircraft acceleration, as that's going to creep into the quality of the gravity data and gravity gradiometry data that you're trying to acquire. As an example, I'm just going to show you from an example from a helicopter survey that was flown in Canada in the mountainous terrains. And we're looking here, this is the Iron Range in British Columbia, and we're looking here at the US border, it's just down here, and we're looking north up towards the Iron Range. This is an IOCG plane. And the topography here is extreme. Down on the valley floor, you're just a few hundred meters above sea level, and the peaks that you're looking at there is at 2 kilometers altitude. Okay, so people, Canadians ski here in winter. So the problem here is that if you want to try to fly this with a fixed aircraft, you have to start fairly far out, because all the aircraft that we use in surveying these days have a typical maximum climbing rate at sea level at something like 65 to 75 meters, vertical meters climb per 1 kilometer flown. Okay. So it takes plenty of kilometers to climb a couple of hundred meters, and if you want to climb 1,800 meters, you've got to start climbing pretty far out. To illustrate this, I'm just taking a profile across this very survey here, and we're looking at the topography here. And we have the topography ranging from 800 meters up to 1,800 meters in that particular profile here. Note that there's extreme vertical exaggeration. There's 14 kilometers across, and there's 1,800 meters up. So there's a bit of vertical exaggeration, but you get the idea. Next, I'm going to show you the actual helicopter trajectory that was done in order to fly this survey. And finally, I'm going to show you here the trajectory, the planned trajectory that one fixed-wing aircraft would have to do in order to acquire this survey. And so you can see that it's quite clear that fixed-wing aircraft do not have the same terrain-following capability as helicopters when you're operating in this extreme environment. And so helicopters definitely have their place. Here's some examples for some helicopter surveying that was done by CGG in Japan, and there's a great poster about some of the results out here in the foyer, so I encourage you to go and have a look at that. Now next, let's have a look at the challenges that face you once you start looking and operating in jungles. Okay. And if there are two words that describe the jungles for you, it is that they're hot and they're humid. And so the heat-related impacts are identical to the ones that's discussed under the desert areas. That you need to cool the electronic equipment down, and you also need to be aware that the heat generates air turbulence that's going to affect the quality of the data that you acquire. As in the polar regions, reliable electrical power may be difficult to find and may necessitate the use of portable generators. And here's some example of the usual dodgy electrical installations that the poor geophysicist and project manager has to deal with the world over. Now, the canopy of the tropical rainforest can cause problems when you're creating a digital terrain model of the survey area for subsequent terrain correction of the observed airborne gravity and the observed gravity gradiometry data. As an example, I'm just going to show you results from a paper that was presented a couple of years ago. This is from a Bell Aerospace FTG survey over, I believe, the exact same eye information that Yaoguo showed some of his inversion results from the QF region in Minas Gerais. And here the authors, this is Braga and al., they decided to see what was the effect of using different terrain models. And so here to the left, you have the terrain model that you can download directly from the SRTM. I believe this one was the earlier 90-meter models, and now we have a 30-meter model available. But the point I'm going to make later on is irrespective of resolution. And on the right, you have the laser scanner DEM, and it has, first of all, a higher accuracy because of the issues I discussed there. But secondly, it has been filtered to remove vegetation. Okay. And so what you're seeing here in the laser scanner DEM is a bare earth model, whereas the SRTM data has not been filtered for topography. And so what you get in the SRTM data model the world over is going to be reflections from canopy. So over heavily forested areas, it is not a terrain model. It shows you the canopy heights and nothing else. What's the effects if you go ahead and use it? Well, here we have the TZZ data that's been terrain corrected. On the left, you have it from using the SRTM data. And on the right, you have it using the laser scanner DEM. And sort of on first pass, they look kind of the same. But then you look at the difference between the two, and here is the difference in TZZ between using the two data sets. And that's not just noise that you're seeing there. There's information in there, and the information is primarily associated with where the forests are. Okay. So be very careful what you use as a terrain model for your terrain effects. Let's have a look at the challenges that face you once you start to venture offshore. Well, whilst you're doing a survey offshore, you have your base onshore. And the environmental factors at the base will be dependent on what are the regions in which you're operating. Okay. But apart from that, there's really no specific environmental challenges to offshore surveying. The largest challenge that comes when surveying offshore is actually the operational challenges that you face. Okay. You have different safety procedures when you operate offshore that you do when you're working offshore. You have different safety procedures working offshore than you do when you're operating onshore. And so there's a managerial and operational issue of transiting a team that's been used to operating onshore to working in an offshore environment. Of course, once you start flying further and further offshore, and the surveys are located further and further offshore, you've got to be mindful of the fact that the actual range of the aircraft starts to become a logistical concern, and that will affect production. Now, let's talk a little bit about the logistics and the challenges that remote and inhospitable areas come to you there. The logistical challenge there is rather than, you can be serving inhospitable areas and they may have unique environmental challenges. And we discussed some of them already pertaining to the polar regions, to deserts, to jungles, what have you. But almost all of them have the same problem, is that they're located in a remote environment. And so supplying and conducting surveying operations in remote areas is actually the common problem that all survey providers face when they are working in these environments. And of course, once you have a base station or a base in a hostile environment, it turns out that there are always high costs associated with maintaining a base of operations. Thank you. Okay, I'll be quick. When I was making this presentation, I suddenly realized that there was not a single formula in here. Okay. Ian takes pride in that, but I cannot go to an ASEG and not present a formula. So here's my formula. Okay. A large part of the cost of doing an airborne survey is associated with the time it actually takes to conduct a survey from start to end. And so it's desirable to fly a survey as quickly as possible. But once you start operating in a remote and inhospitable terrain, the risks of having delays go up proportionately. More things can go wrong and they take longer to fix. Okay. Likewise, you'll have limited time and a weather window to operate in. And finally, you'll find that if you're so remote that there are no nearby weather stations, then you have imprecise weather reporting and few alternate airports. And that's going to force you into having a very conservative flight plan, which can limit your operation. Likewise, with logistics, the ease of access to the base of operations is very important. It doesn't really matter whether you're in a remote location if it's easy to get to the base, so that you quickly can get supplies in there. If a base is hard to reach, then it doesn't matter if you're in a hostile environment, it's going to increase the risk of having delays. So as for conclusions, well, over the past 15 years, we've flown airborne gravity and airborne gravity surveys successfully and are acquiring them successfully in the most inhospitable areas of the Earth. Okay. Surveying in these inhospitable areas can pose unique environmental challenges for each area, and we've touched on a number of them here in this presentation. But common to all of them are that most of the challenges are in fact related to the logistics of supplying and conducting survey operations in remote areas. So I just want to acknowledge Srinivas and Stefan Kuna from Bell Geospace, Craig Gannison and Mark Dransfield from CGG Multiphysics, and Malcolm Argyle and Stefan Iliev from Center Geophysics for providing some fantastic images of their survey activities, and also having spent time with me discussing these challenges that we all face in this space. Just some quick references that was in this paper. And finally, I just want to thank you all for coming here today, listening to my talk, and if there are any questions, I'll be happy to answer them later. Thank you.
Actually, Ashbourne, you've got the chance to answer the questions now, if you like. Okay, if Yaoguo and Helen and Ian could come up. And questions?
Mark Dransfield from CGG. Ian, you showed the constrained inversion where you said, I believe, the magnetics was used to constrain the gravity inversion. Did you try going the other way at all?
No. Had I had time, I would have. And I suspect that that keel that you saw in the gravity might have shown up in the mag, but I didn't do it. So.
Yes, that was the reason for my question, because I don't know which one's right, obviously, but certainly there looked like there was more continuity in the gravity model than in the magnetic model. So that keel, like, which you guess you referred to.
Yeah, I guess you're kind of bringing up a point that I like to make about this, is that the non-uniqueness is way bigger than people think. And the fact that they're so different that's sort of the fidelity you're going to get. Now that was AGG only in that particular one, so I actually don't expect much fidelity at that depth. And so the model is quite free to put things in where it would like and not like. And so there aren't a lot of constraints to control that. So just introducing a little bit of that susceptibility constraint completely changed it at depth. But near the surface, within the top 200, 250 meters, it stayed the same. It's very consistent. So I wasn't too surprised by it. But again, it comes back to my point, is when you're running inversions, we believe, and it's a self-interest position I'm putting out there, is you need to run a lot of them so that you can start to get a feel for what the limitations. And also remember that every one of those inversions produce exactly the same output. So from the data alone, you can't tell the difference.
Hi, I just wanted to, from Gondwana Geoscience, just wanted to pick up on what appeared to be a common thread from the first three talks, and that's, it probably is a whole, well, it's worthy of a workshop on its own, I guess, and that's the components and to use in inversions, and all of those talks were showing that GZ or GZZ was basically required, seemingly, to sort of to get some of the better responses. I didn't want to sort of contradict Helen's talk because it had my name in it, but just referring to that the slide that you showed, which showed the declining curves for the different components. One of the reasons you don't get, I've noticed from working with data and seeing other people's examples, is that with the horizontal components, you just don't seem to get as good a coupling, seemingly, with the sources, and so there's less power available, seemingly, with those components for doing the modelling. And so even though you have more noise in the ZZ, you also have more signal. So, and that's actually is still the most driving and the most important thing. And I think that is why I think in the case of Yaoguo's example, where you needed the GZ in order to be able to, because you end up with this very smooth result, and it's probably just from weak, I guess, perhaps coupling with the objects. So. I mean, it's a subject for another workshop, whether to use which combinations of gradients or invariants or different things like that to work with. But I just wanted to point that out as a common thread.
Good question,
Matt. If you don't know me, my name's Alan Morgan. I worked previously for Fugu Gravity-Magnetic Services, and I worked with Richard Liu on a joint inversion algorithm where you use multiple components to get to the same answer. And we actually had a similar issue that Ian was addressing, is that the software actually will see the error as a single point or a dimensionless object when treating the grid as a whole, and it will try to iterate and reduce that standard deviation of error regardless of wavelength. The key to reducing the number of iterations and to speeding up the inversion process is to try to weight it with some wavelength factor that spreads the error out over distance rather than treating it as a single point. So I have personal experience seeing that it actually will come to the 90% solution a lot faster if that is involved, rather than trying to come up with a non-geologic solution that has all the high frequency content in it.
Yeah, if I can comment on the first comment, I don't think we should leave here with impression that GZ, vertical gravity, is requisite. I think that comes in just because the commonly recognized in lack of very long wavelengths signal in the current gravity gradiometry data. So if someone produces a system that actually is able to capture the long wavelengths component, then that actually would eliminate the need for adding the gravity data. So I think that's a particular scenario, and I don't think that has a generality. The second comment I want to make is that about the error and also different components. One thing that has not been discussed here, I think that's just because of the time limit of the presentations, that we talk about error, we talk about multiple components. Implicit to that is the different standard deviation of the errors in different components. That comes in, that will change the solution dramatically. And the case we did with the quadrilateral behavioral study, CC, in fact, spent most of time for that data set on coming up with a reliable estimate of the noise level for different components. They are not uniform. So the best result is actually obtained by iteratively estimating the error and putting that different error levels to different components into the inversion. So I think that's one component. I just want to bring it up. Component meaning the aspect of the inversion of quantitative interpretation that needs to be taken into consideration.
There's certainly no suggestion for me that you shouldn't use horizontal gradients at all. Just an observation.
Perhaps the last question.
I think it's horses for courses.
David Pratt from Tensor Research. I'd like to pick up on the point that you raised. One very important thing about any component that has a horizontal component is telling you information that's off the flight line. Is it on the left side of the flight line? Is it on the right side of the flight line? And anything we can do to incorporate that into the inversions, I believe, is quite important. Ian, the example you had where you argued with your colleague about whether the horizontal versus the other one, I thought geologically the one you didn't prefer was more coherent in the final sense. And I think that horizontal information, we mustn't throw it away because it's telling us something away from the flight line. GZZ only tells us this direction, very little about what's off to the side, except from the next flight line.
I'm just going to sneak in quickly because I know of several discoveries that have been made where the drill holes have been sited on inversions of the curvature components alone with no other information.
It's basically time for a break. We come back at 15:05, 5 minutes past 3.